Hello, and welcome to Course 7 of the Verifier training for the Oregon Greenhouse Gas Reporting Program. If you have any questions about this course, please email us at 3pverify@deq.oregon.gov. This presentation is for selected subparts of 40 CFR 98. Course 8 will cover process emissions from additional subparts and sectors that are specific to Oregon reporting. As a reminder, the information presented in these slides does not replace the verifier's responsibility to know and abide by DEQ's Greenhouse Gas Reporting Program and third-party verification regulations. Please read the regulations, and if any information conflicts, the regulation takes precedence. In this course, we will be discussing the verification of process emissions reported under subparts H, N, Q, and V of 40 CFR Part 98. There are multiple sources in the state of Oregon that report under these subparts. We will begin with subpart H, cement production. Portland cement is the most common type of cement in general use around the world as a basic ingredient of concrete, mortar, stucco, and non-specialty grout. It was developed from other types of hydraulic lime in England in the early 19th century by Joseph Adpin and is usually made from limestone. Oregon has one cement production facility, that's Ash Grove Cement Company. This slide shows the material flow at a typical cement plant. In the first step, raw materials are received and stored. The second step is thermal processing, where all of the process emissions and most of the combustion emissions are produced. Third and final steps include final production preparation, packaging, and storage. In this slide, we are looking at a more detailed cartoon version of a typical cement manufacturing facility. The preheater and cement kiln, seen boxed in red, are the primary emissions units in typical cement manufacturing facility. The GHG emissions are from the combustion of fuels in the preheater and the cement kiln, and from CO2 process emissions from the calcination of limestone in the preheater and kiln. Approximately 60% of CO2 comes from the calcination process, and about 40% comes from the combustion of fuels in the typical cement manufacturing process. Here we are looking at some common production ratios. There is enough variability in annual cement production that it should not be assumed that they operate continuously or almost continuously. Cement plants must report carbon dioxide process emissions from their cement kilns, carbon dioxide, methane, and nitrous oxide emissions from combustion of fuels in both the preheater and cement kiln, and carbon dioxide, methane, and nitrous oxide emissions from combustion of fuels in any other stationary combustion units at the facility. The preheater and kiln section of the facility are the only areas where process emissions occur. There are no assumed process emissions upstream or downstream from the preheater and kiln. When using CEMS, it is assumed that all process emissions are captured by the CEMS, such that any additional process emissions released after the kiln are assumed to be zero. There are two possible calculation methodologies to choose from in subpart H, namely CEMS and a mass balance method. The only cement manufacturing plant in Oregon currently uses CEMS and must follow the Tier 4 requirements in subpart C of Part 98 and report the combined CO2 emissions from process and combustion from a common stack with CEMS. For that reason, the focus of the next few slides in this training will be on the requirements for CEMS. There are some common issues with CEMS reporting that verifiers should be aware of. Verifiers should ensure all monitoring and QA/QC requirements described in 40 CFR 98.84 are being followed. Verification of CEMS data was also discussed in Course 2 titled Stationary Sources, General Information, and Stationary Combustion. The verification approach of CEMS data focuses on ensuring the reporter has completed all of the required quality assurance and all of the maintenance requirements for their CEMS equipment. The verifier should review on-site QA, QC, and maintenance records for dates to ensure the QA procedures were completed in accordance with the required schedule and check the linearity, cylinder gas audits, and relative accuracy test audits for the entire year. The verification requirements for missing SIMS data when reporting under Subpart H are the same as those for stationary fuel combustion Tier 4 calculation methodology. For missing data, you will need to verify that the facility followed the missing data procedures provided in the applicable regulations. As a verifier, you will need to verify that any interim procedures used by a facility have been approved and that the facility did not deviate from those procedures. Emissions from biogenic fuels must be reported separately from emissions that are produced from the combustion of fossil fuels. If biogenic fuels are combusted, then there are 3 reporting options to report fossil and biogenic fuels separately. The first option is to measure biomass fuels accurately so you can claim those resulting emissions as biogenic. The second option is to conduct quarterly stacked gas sampling. This relies on good fuel management and tracking so the ratio of biogenic CO2 in the flue gas can be applied to the total flow on an annual basis. The third option is that the biogenic fuels are counted as fossil-derived fuels. This is in the case that they are not measured separately or there is no data on the amount combusted. There are some considerations for fuel type and quality that verifiers should be aware of. The amount of fuel combusted should be audited with the fuel purchasing records to ensure the accuracy of the reported combustion emissions. Tires have different characteristics than other fuels. The calculation requirements for the combustion of these fuels are described in Subpart C. They are not specific to Subpart H. Not only are tires a very high energy fuel, but some cement plants are paid to burn tires, making them a very low cost fuel. On-site inventories of tires are not common practice, and they're almost always stored in large box containers. A good practice for verifiers is to understand how the operator determined the production data to determine where errors may have occurred. Verifiability of covered product data is impeded when operators do not sufficiently describe the methodology used. A description of the steps taken to measure and report covered product data must be included in the operator's greenhouse gas monitoring plan, so you can conduct a preliminary risk assessment and develop an initial sampling plan. During site visits, review and follow all safety guidance provided by the facility. Check all data inputs used for emissions calculations. Observe metering devices. Check calibration records. Visit all emissions units. Review fuel and chemical purchasing receipts and invoices. And review production records and compare to previous year's records, noting any anomalies. We will now discuss Subpart N, glass production. Regulation applies to glass production facilities that make glass from a mixture of carbonate-based and non-carbonate-based raw materials. It does not apply to glass-making facilities that simply recycle glass. Facilities must be producing glass from carbonate-based raw materials to be subject to reporting. However, the facility may produce any type of glass product, such as flat glass, container glass, or fiberglass. Oregon has 2 glass manufacturing facilities. We are now looking at the material flow for a glass manufacturing facility. Note that the glass kiln is the only area with process emissions. The emissions from the glass kiln arise from 2 sources. The first are the combustion-related emissions from the burning of fossil fuels. The other source of emissions comes from the calcination of carbonate-based raw materials, a process that releases carbon dioxide. Since the emissions come from the carbonate-based raw materials, the amount of processed CO2 emissions will vary from one plant to the next depending on the amount of carbonate-based raw materials used in the glass recipe. One other point to note is that facilities that use a higher percentage of cullet in their production process will have lower levels of CO2 process emissions compared with the amount of glass produced. Cullet is recycled or waste glass that does not contain carbonates and is introduced or reintroduced into the raw material supply stream. In this slide, we are looking at a cartoon image of a typical flat glass manufacturing facility. There are similar inputs for container and fiberglass manufacturing. However, the shaping process for container and fiberglass is different when the molten glass exits the furnace. Much like cement manufacturing, total emissions must include CO2 process emissions and emissions from all stationary combustion units. All process emissions are assumed to occur in the furnace. To verify the annual emissions calculated using the mass balance method, verifiers must confirm that the data used in the calculation is accurate and complete. Verifiers should review all monthly measurements, purchase records, and testing results of raw materials for accuracy and completeness. Verifiers should review how the facility determined the amount of carbonate-based raw materials charged to each furnace. Verifiers should also check to ensure that the scales used to make the measurements are in compliance with applicable calibration and maintenance requirements. The measured amount of carbonate-based raw materials should be compared to the original raw materials purchased in inventory records. If the measured amount of raw material differs from that determined in the original purchase orders and invoices, then the verifier should follow up with the facility to determine why there is a discrepancy between the two records. There are a few specific things you'll need to check, including raw material inputs in the mass fraction and calcination test, if a default of 1 is not used for both mineral mass fraction and the calcination fraction. That means there is no testing requirement for this calculation methodology as long as both defaults of 1 are used in equation N1. Second, review the analytical data to determine whether the average mass fraction of the carbonate-based materials is correct. For example, do they have mass fractions for every month? Verifiers should also determine whether the measurements were made in accordance with the methods specified in 40 CFR 98.144b. Similarly, if operators use their own site-specific calcination fractions instead of the default value of 1 provided in subpart N, then the operator must have documentation to support the values they used in the mass balance calculation. The facility must use an industry consensus standard that uses X-ray fluorescence test or other enhanced testing method. If a verifier is unsure whether a particular method is acceptable, they should consult with DEQ staff. Next, you should verify that the values used in the mass balance calculations are correct and are correctly entered into EGRET, EPA's reporting tool. Finally, you should recalculate the CO2 process emissions using equation N1 to ensure no calculation errors have occurred. If there is a case of missing data, the reporter should follow all steps and guidance in 40 CFR 98.154 for missing data estimations. During site visits, review and follow all safety guidance provided by the facility, check all data inputs used for emission calculations, observe metering devices, check calibration records, visit all emissions units, review fuel and chemical purchasing receipts and invoices, and review production records and compare to previous year's records, noting any anomalies. We will now discuss subpart Q, iron and steel production. There are combustion emissions from a variety of sources, including but not limited to byproduct recovery, coke oven battery, combustion stacks, blast furnace stoves, boilers, process heaters, reheat furnaces, annealing furnaces, flame suppression, ladle heaters, etc. Here we can review a generalized figure showing carbon balance process where carbon-containing inputs feed into the process. Some carbon exits and carbon-containing outputs, with the remainder emitted as CO2. There is a wide range of inputs and outputs in iron and steel production. So all of the carbon in the inputs is estimated as CO2 out of the stack, except for any carbon that remains as metal in carbon outputs. There are several equations associated with subpart Q. The first 7 equations are for carbon balance. As an alternative to carbon balance approach, equation 8 is used for developing a site-specific emission factor. As with almost all other process emissions, report verifications, it is important to review all carbon-containing inputs and outputs and any other data that can be used to ensure the calculations and reported emissions are accurate. If any input or output category contributes less than 1% of the total carbon, it can be excluded. There are many variables in equation Q5. All variables input into the equation should be verified to be accurate and complete. The carbon content data must be measured or supplier provided and cannot be estimated. Missing mass data for inputs and outputs can be replaced using either best available data or maximum throughput data depending upon amount of missing data as described in 40 CFR 98.175. All input and output data, all calculations, and all monitoring and QA/QC requirements described in 40 CFR 98.174 should be reviewed and verified. During site visits, review and follow all safety guidance provided by the facility, check all data inputs used for emissions calculations, observe metering devices, check calibration records, visit all emissions units, review fuel and chemical purchasing receipts and invoices, and review product records and compare to previous year's records, noting any anomalies. The final subpart to be discussed in this training is subpart V, nitric acid production. Subpart V applies to any nitric acid production facility with 1 or more trains to produce nitric acid of any strength. A nitric acid train produces nitric acid through the catalytic oxidation of ammonia. Prior to 2018, this subpart only applied to production facilities that produced weak nitric acid, 30 to 70% in strength. Emissions from stationary combustion should be reported under subpart C. Process emissions should be reported under subpart V separately. There are a total of 7 equations included in subpart V. We will review these and how to verify their inputs in the next few slides. As mentioned previously in this and other trainings, the GHG monitoring plan should be reviewed in all verifications. Equation V1 is used to calculate an average site-specific emission factor for each nitric acid train and uses the results of the performance test described in 40 CFR 98.223b as the variables in the equation. Equation V2 is used to calculate the abatement utilization factor for each nitrous oxide abatement technology for each nitric acid train. Verifiers should verify that all equipment used for direct measurements is calibrated and maintained as described in 40 CFR 98.3I. Abatement utilization identifies a fraction of production that occurs when abatement is used. Here we are looking at the 6 nitric acid train configurations that may be encountered at a nitric acid production facility. The process trains are represented by rectangles, while performance test locations are indicated by stars. Abatement technologies are represented by squares. Abatement technologies primarily consist of non-selective catalytic reduction of the effluent in the process stream that will become the stack gas. To calculate the emissions in scenario A with 1 abatement technologies, reporters should use equation V3A. To calculate emissions in scenario B with no abatement technology after the test point, like in scenario F, reporters calculate emissions with equation V3D. To calculate emissions in scenario C with two abatement technology devices in series, reporters should use equation V3B. To calculate emissions in scenario D with two abatement technologies in parallel, reporters should use equation V3C. To calculate emissions in scenario E with two trains monitored together, reporters should calculate emissions with V3A. To calculate emissions in scenario F with no abatement technology after the test point, reporters should calculate emissions with equation V3D. In this slide, equation V3A, V3B, and V3C can be reviewed. This table shows if destruction efficiencies, abatement utilization factors, or fraction control factors are needed for the V3 equation. Equation V3A is for one abatement technology after test location. Equation V3B is for 2+ abatement technologies in series after the test location. Equation V3C is for 2 or more abatement technologies in parallel after the test location. And V3D is for no abatement technologies after the test location. Fraction control factor is only used if two trains run in parallel and represents percent of total emissions sent to abatement technology. Equation V3A is the basic equation format. Equations V3B, V3C, and V3D are derivatives of it. Destruction efficiency is a fraction of nitrous oxide sent to an abatement technology that is destroyed and is necessary to quantify the actual effect of any abatement technology. Abatement utilization factor is a ratio of nitrous oxide sent to an abatement technology compared to the total nitrous oxide produced. Fraction control factor is a quantity of nitrous oxide that is sent to a particular abatement technology. Missing production data can be replaced using either best available data or maximum production data, depending on reporting year and amount of missing data. Equation V4 is used to determine the annual nitric acid production emissions combined from all nitric acid trains at the facility. Like the verification of all other subparts, verifiers should verify all input and output data, all calculations, all calibration and maintenance records for equipment, and ensure that if there is missing data, that the procedures for estimating missing data described in 40 CFR 98.225 are followed. During site visits, review and follow all safety guidance provided by the facility, check all data inputs used for emission calculations, observe metering devices, check calibration records, visit all emissions units, review fuel and chemical purchasing receipts and invoices, and review production records and compare to previous year records, noting any anomalies. This concludes Course 7 of the Third-Party Verification Training Program. Thank you for attending this training for process emissions reported under subparts H, N, Q, and V. If you have any questions about this course, please email us at 3pverify@deq.oregon.gov.